Okay, let's solve n queens. N queens we're going to solve using our generic backtracking solver, just like we did subset sum. And in fact, I encourage you to watch the video for subset sum and also try to solve subset sum yourself before watching this video. Cool. So here we are with n queens. And to remind you how we're going to try to approach this problem, we're going to try to place a queen in the first column and then recursively place them in the rest of the columns. So what a move amounts to is placing a queen in a column. That would be a move. And then the state is going to be a 2D, a 1D list of the locations, the row call locations of our queens. Okay, cool. And then so we recursively try to place here, but the constraint enforces that no two queens attack each other. So we would eventually get to here and so on. And of course, we get to a solution state eventually that might look something like this, and that is a solution state. This is not a solution state, but it is it satisfies constraints because no two queens are attacking each other right now. Okay, so those are the basics. Again, our state is going to be a list of the queen positions, and our moves are going to be in a single column, adding each of the possible places we can move in that column. Great, let's go ahead and start writing this, okay? So actually what we're going to do is first we're going to run it. So we come here and we copy this code and we paste it here and we try to run it. And it doesn't run for the same reason as before. We need to get the generic code that we're extending, so we'll get those classes, put them up there. Go ahead and run this. And sure enough, this is running over 7, and here's a 7 queen solution. It looks like no queen is attacking any other queen, happily. We required to make 10 states and only 7 moves. Without constraints, we still found our solution, but with 53,000 almost states and quite a bit more time. Okay. If you look at the moves are placing queens. There's the one at 0, 0, the queen at 2, 1, the queen at 4, 2, row, call. The rows are all over the place, but look at the columns. Column 0, column 1, column 2, column 3, 4, 5, and 6. So what happens is each move places a queen in the next column over, and we do that until we get to the end. Now that we understand that, and also let's just do n queen solver of 1 just for kicks. You run that, sure enough, if you have a 1-by-1 board, it's just 1 queen. 2 can't work, 3 can't work, and finally 4 is the next one that works. And we've done this in our examples over and over. And there's our moves. 1, 0, that's row 1, column 0. 3, 1, row 3, column 1. 0, 2, that's this one. And 2, 3, that's that one. So now we're going to do what we did last time. We're going to go ahead and delete that code. And we're going to go ahead and delete this code. Okay, so go ahead and great, okay? And we'll go ahead and run it, and it fails because it takes one positional argument, which would be n. So let's go ahead and create our constructor, and our constructor is going to take a self and n, and we're just going to go ahead and note that self.n is n, okay? And that would be that, except of course we also have to create our start args and our start state. Okay, so our start args is simply n, but if you do that, remember a singleton tuple, add that comma, and our start state is something. Okay, well, what goes into an n queen start state? Turns out all we need to store is the list of queen positions we've made so far. Okay. So n queens state, and it will be helpful for us to share n as well. So we're going to put n in there, and the initial queen positions are that we haven't stored any queens yet. So the state here, queen positions. So self.n is n, that's just useful for us, and self.queen positions is queen positions. Cool. Okay, so now we run this. Well, we didn't implement is solution state. So, whoops, what am I doing? Is solution state. And so you take yourself and you take a state and the question is if this is a solution state. Okay, and for that, well, to begin with, we know that if we haven't placed down n queens, it can't be. So if the number of queens that we have placed down is less than n, then it can't possibly be a solution state. Okay. The other possibility is just to confirm that no two queens attack each other. So if we have n and no two queens attack each other, then sure enough, it's a solution state. So for each starting queen, okay, so we'll get that starting queen's position. So the queen positions are the positions of all the queens in this state. We'll get the ith queen and we'll have its position, and then we'll compare the ith queen against every single queen before it. Okay. So now we have the jth queen, which is every queen before it. So we're comparing every queen to every other queen. Okay. And we're going to assume that we have a method called queens attack each other. And it takes a row and a call, another row, and another call. So that's the position of the first queen and the second queen. And if that is true, that those two queens attack each other, then this can't be a solution state. Otherwise, this is a solution state. Cool. So again, we're just going to compare every queen we've placed down to every other queen we place down, and if any two attack each other, it can't be a solution state. So now we have to have the queens attack each other method. Okay, so for that, we'll go up here. Def queens attack each other of row 1, call 1, row 2, and call 2. Okay. And notice this doesn't need self. It really isn't helpful here, so this becomes a static method. Okay. And what we're going to return are the ways queens can attack each other. They can attack each other if they're in the same row. So if row 1 is row 2, they attack each other. Okay. Or if what? In the same column. Column 1 equals column 2. Or they're in the same diagonal heading up. Okay. So if they're in the same diagonal heading up, I'll do this. Okay, get rid of that. Go here. Oop. There we go. All right. So this queen and that queen are in the same diagonal heading up. So this queen is in row 0, 1, 2, column 1. And this is in row 0, 1, column 2. And so the sum of the row plus column here is 3. And the sum of the row plus column here is 3. And the sum of row plus column will be the same as we head up. Why? Because when we head up on this diagonal, the row gets one smaller and the column gets one bigger. So their sum remains the same. That's true on any diagonal. On this diagonal, which is only one value, the sum is 0. On this diagonal, it's 1. Here it's 2. Here it's 3, 4, 5, and 6. So what we test for is that row 1 plus col 1 equals row 2 plus col 2. And that's a test if they're on the same upward facing diagonal. What about a downward facing diagonal? Okay, so here the sum definitely does not remain the same. Okay, but what's interesting is the difference remains the same. So the difference between row and col here is 0, right? This is row 1, col 1, so 1 minus 1 is 0. Row 2, col 2 is 0. They're all 0 on this diagonal. What about on this diagonal? This is row 1, column 0. Their difference is 1. Row 2, column 1, the difference is 1. 2 minus 1. The difference is always the same because to go down, we add 1 to the row and add 1 to the column, so the difference remains the same. So if we test if row 1 minus col 1 equals row 2 minus col 2, that'll test if they're on the same diagonal. Cool. And now we haven't done get legal moves. Okay. So let's go ahead and do get legal moves. So if we're in a state, first off, what column is the next column we want to add in the state? Well, let's go back and look at this again. So if we were in, say, this state right here, our queen positions would be a list with 0, 0, and 2 comma 1. The next column we want to do is column 2, which happens to be the length of our queen positions, right? The length of the queen positions is 2 because we placed 2 queens. And because those are in columns 0 and 1, column 2 would be the one we want. So what we just said here is the column is going to be the length of our queen positions. Cool. If we're done, then we have no more legal moves. Okay, so now we're not done. So what we want to do here, let's go back here, is the legal moves are row 0, column 2, row 1, column 2, row 2, column 2, and row 3, column 2. And you might say, hey, wait a minute, that's not a legal move because that queen attacks it. There's a difference between a legal move and violating a constraint. You certainly can put a queen there. However, if you did, it would violate the constraint that queens are attacking each other. That'll be handled by check constraints later on. So we want to have a list of 4 tuples, 1 for each row in this column. And to do that, we will return a list of tuples, 1 for each row in the column. That does that, right? So for each row in the column, we'll fix the column to be that column, but use each row. Cool. And now we don't have do move. Okay, so what is do move going to do? Well, def, do move, self, you're in a state, you're making a move. Let's think about the state. A state is just, well, n, which is the same, and queen position. So we just, to do a move, remember a move is just a row column tuples. Like here, if I go here, it's do move 0, 3, pardon me, 0, 2. And what you'd want to do this move is add it onto the queen positions for the new state. That's all you have to do. So my new queen positions will be my old queen positions plus the move. And you have to put it in a list because we're adding it to a list that way. Cool. Then we create the new state, which is a new state of n remains the same, but I'm going to use these new queen positions. And that's it. That will create. That'll do the move. State satisfies constraints. This method is very similar to is solution state. And in fact, we could actually essentially copy this code and paste it, in which case we'd put it in its own helper method. But we're not going to do that because we don't actually have to check if every queen attacks every queen. Okay, we can be more clever about that because we know that we're checking as we're going, so that the only queen that we actually have to check is the last queen that we added. Okay, so we'll get the position of the last queen that we added. Okay, that's the last queen. And then we'll go for every queen up into and not including that last queen. And then it'll look very similar to this code down here. Okay, so then we will go ahead and say if the last queen attacks any prior queen, then we did not satisfy the constraint. Otherwise, we did. Okay. Now you might say, wait a minute. The same logic should be true that when we get to a solution state, we should only have to do that test there because we tested the queens as we're going on satisfies constraints. That's actually completely true. The problem is that we can actually send in a Boolean to turn off constraint checking. To turn off backtracking, essentially. In which case, we'd get to a solution state, and if we didn't have this code right here, then we would permit illegal solution states. We'll actually watch that happen in practice. But we're done beautifully, except we have the same problem we had before, that our repr in our state is not printing this out in a pretty way. So here you might think what we would do would be similar to what we did for subset sum. You might think we do repr of self return, not in the solver, inside the state, and return maybe the stir of self.queen positions. Something like that would be like subset sum. And it's not great because I don't think that's what people are looking for when they're thinking about the solution to an n queens problem. I think they're looking for something that looks like a board. Okay, and for that, what we'll do is we'll create a 2D we'll start with a board, which is going to be a 2D list of what? It'll be a 2D list of dashes. Create a list of dashes, okay? And we'll have it, that's a list of n dashes, okay? And then we'll put, actually it's a tuple of n dashes, then we'll, I'm sorry, it's a list of n dashes that then we will put n of those together to go ahead and give us a 2D list of dashes. So if we do this right now and say we just return the board, and we have a non-static list. So what we had to do there, since the board is all dashes, you can't return that 2D list. So we will do stir a board. That's not what we wanted. We wanted to separate all of these rows of dashes with new lines. So we'll do new line. Oh, come on, editor. Dot join, and we're going to join would be the board itself. But the problem is this has to be strings even here. So what we'll do is we will separate the dashes by spaces and join each row. Okay, and now I have to go ahead and put a bracket right there. Cool. Okay, so now our boards are just dashes, but that's happily at least a 2D board. But now you wanted to actually go and put the queens where they belong. Sorry for the low-level details here, but there's your code, and there's what it's doing. You can kind of stare at that for a while and figure out what we're doing. Okay, cool. So now to put the queens there, we'll do for every one of our queen positions, all we'll do is say that the board of that, instead of a dash, is a queen. And look at that. We now have our queens, which is really nice. Our moves are 1, 0. Those are the moves you have to make to place these queens down. But excellent. So that worked. And we have n queens working nicely. And that should hopefully be enough for you to delete this code and write it yourself. You have the video to refer back to, and of course you also have the notes. But it's important that you be able to write this from scratch. That's the expectation for the course. So I hope this helps. Good luck with it. Have fun.